Hello mathematicians. Today we see a part C problem asked in CSAR June 2014. This is a very interesting problem regarding inner product. So let U, V, W be three vectors in an inner product space V. Okay. So whenever they are saying it is an inner product space V, we always imagine as R square, R2 or R cube something, and we consider vectors from R2, R3 so that the problem will give better sense to us. Okay. Okay. Now we are considering three vectors from inner product space V, and the vector satisfies norm. Okay. Norm of each of them is 2. Further, inner product UV equal to 0. What is the meaning of inner product U comma V equal to 0? It means that U and V is orthogonal to each other. One is perpendicular to the other, then only we'll get their inner product is 0. Okay, very good. Then inner product U comma W equal to 1 and inner product V comma W equal to minus 1. Okay. Then which of the following options are true? Note that it is a part C problem, so more than one option can be true. Now first we make a simple observation. Note that none of U, V, W are 0. Okay, if one of them is 0, then this cannot happen. If U is 0, then this we should have got 0. If V is 0, then we should have got this is 0. Okay, inner product 0 with anything is 0. Again, if W is 0, then we will get this value is 0. Okay, therefore U, V, W, all of them are non-zero. Okay, now with that is one just a simple observation. Using this we calculate each of these option. We'll check each of the option. So first we have to calculate what is norm of W plus V minus U. Okay, so that is it's a straightforward calculation, so we do it step by step. So norm W plus V minus U square, norm square is equal to so this is generally true, norm inner product W comma W equal to norm W square. Okay, using that we get norm W plus V minus U whole square equal to inner product W plus V minus U, W plus V minus U. Okay, now norm is a bilinear map. Bilinear means you can split the sum like this. So this inner product W comma this element. Okay, second, then V comma this element. Again, then this minus I have put it here. Then U comma W plus V minus U. We can split it like this. Then again, each of them can be further divided. So W comma W plus inner product W comma V, then minus W comma U. So these three terms we get from this one term. Now similarly this we get inner product V comma W plus inner product V comma V minus inner product V comma U. So we get these three terms. Similarly these three terms we got it from this term. Okay. Now you see we are given norm U equal to 2. So norm U square equal to 4. But what is norm U square? Norm U square equal to inner product U comma U. Okay, so inner product U comma U is 4. Similarly, inner product V comma V also 4. Inner product W comma W also 4. Since all these norm have the same value, and we have these other values also. So if we substitute all these values in this equation, we get the sum value is 8. Okay. Okay. Now maybe this makes better sense to you. So we have all this value we have. So norm U square equal to 4, norm V square equal to 4. Similarly, norm W square equal to 4. So we can substitute all these 9 values, all these values here, we get 8. Okay, so norm W plus V minus U square equal to 8. That means that norm W plus V minus U equal to root 8. Root 8 we get plus or minus 2 root 2, but norm is always a non-negative number, so we take the positive square root, we get 2 root 2. Okay, so we get the first option is correct. Now as I said earlier, U and V has inner product 0. That means that they are orthogonal to each other. Okay, and each of them has norm 2. u also has norm 2, v also has norm 2. So if you divide by 1 by 2, then what we will get, what is norm 1 by 2 u? So norm 1 by 2 u equal to, we get 1 by 2 times norm u from by the norm definition. We get 1 by 2 times 2, we get 1. Okay, so this what it shows is norm of 1 by 2 u is 1. Okay, similarly norm of 1 by 2 v is also 1. So what we get? So this, so if u and v are has uh, sorry, if u and v is perpendicular to each other, then 1 by 2 u and 1 by 2 v also has the inner product 0. Therefore we get this vector and this vector has inner product 0, and each of them has norm 1. Therefore this is an orthonormal basis. Therefore these two vectors are form a orthonormal set of cardinality 2. So if it is an orthonormal set of cardinality 2, it is a orthonormal basis for a two-dimensional subspace of V. Okay. For example, you take the vector space spanned by these two vectors. For that vector space, it will be a orthonormal basis. Okay. Now we come to the third option. We have we want to prove W and 4U minus W are orthogonal to each other. What we have to prove? We have to prove that inner product W comma 4U minus W is equal to 0. That again very simple calculation. So inner product W comma 4U minus W equal to inner product W comma 4U minus inner product W comma W. Okay, now we can take the 4 outside and we get 4 times inner product W comma U minus WW. Now in the problem it is given the inner product W comma U equal to 1. So we get 4 minus 4 0. Okay, therefore option 3 is also correct. Okay, now option 4 is the little tricky one. We need some geometrical idea about inner product. So we notice that if inner product u comma v equal to 0 means it is orthogonal. Orthogonality is a geometric property. Similarly, we want to understand what is the meaning of other inner product values. Okay, so as I said in the beginning, we take v to be R2 and we construct three vectors u, v, w satisfying all this given condition, but they are linearly dependent. Okay, if you take R2, okay, if you consider R2, these three are non-zero vectors. Okay, but R2 has dimension only 2. Okay, therefore in a two-dimensional vector space you cannot have three linearly independent vectors. Okay, so we will get, if you in R2, if you can find vectors satisfying these condition, they have to be linearly dependent. Okay, because R2 has dimension 2, in a two-dimensional vector space maximum there can be two linear independent vectors. Okay, so that is our idea. Okay, in R2 we construct vectors satisfying all the given condition. That requires little bit geometric idea, but again that idea can be used in another problems also. Okay, so let's see how to do it. So we consider v equal to R2. We need three vectors u, v and w, right? So I take, and each of them has norm 2. So I draw the circle with the radius 2. Then if you consider any point on this circle, this is a circle of radius 2 with the center at 0 comma 0. Okay, now if you take any point on this circle, all of them will have norm 2. Okay, that is the meaning of norm. Okay, now I need three vectors u, v, w. First what I need u inner product. Let me rewrite the conditions here. We need u comma v satisfying u comma v equal to 0, inner product u comma w equal to I'm sorry, 1. We want inner product v comma w equal to minus 1. Okay, we need three vectors in R2 satisfying this condition. Each of them are lying on this circle. So for this u and v, for u I take 2 comma 0. Okay, for v I take 0 comma 2. Then they are perpendicular to each other. Okay, therefore their inner product will be 0. We can directly calculate the inner product also. How do you calculate the inner product of 0 comma 2 into 2 comma 0? So 0 into 2 plus 2 into 0. So basically that is 0. Okay, Now we need a W. Okay, so we got U, we got V. We need a W satisfying these two conditions. Okay, okay. Let's see what is this condition means. V comma W, U comma W equal to 1 and V comma W equal to minus 1. Let's see what is the meaning of those conditions. Okay. Uh, okay. Let me write. Let me. So okay, that is not a nice place to write. Uh, Now inner product, we get inner product U comma W should be 1. Okay, right. So what is the definition of inner product? Inner product of U comma W equal to inner product of U, inner product of W times angle between U and W. Okay, so this what is theta? Theta is the angle between angle between U and W. For example, if I take a W, this is my W here, then this angle between U and W, this is what we call theta. Okay, right. Then this is the definition of inner product. Now this implies inner product U comma W equal to what is norm U? We get norm U should be norm U is 2 and norm W is also 2 times cos theta. Correct. So this implies inner product U comma W, we know it is 1. Okay, this implies 1 equal to 2 into 2 into cos theta. This implies cos theta equal to 1 by 4. This implies theta equal to cos inverse of 1 by 4. Why we are doing this calculation is we want to see on this circle we want to find where we can put a W. That is a question. So if I find a W, the angle W, so if I find a theta, then I know the point W. Okay, because then I can put a W such a way that it makes the angle theta with the U. Okay, so that is our idea. What is our idea? From the given condition U comma W equal to 1, we find theta so that we can explicitly say what is W. Okay, this condition U comma W equal to 1, U comma W equal to 1 says that the angle between theta and U, so the angle theta between U and W has to be cos inverse of 1 by 4. Okay, so what is cos inverse of 1 by 4? You see, this is cos x curve. Cos 0 is 0, cos pi by 2 is, sorry, cos 0 is 1, cos pi by 2 is 0, and in 0 to pi by 2 it is a decreasing curve. So somewhere it will have the value 1 by 4. Okay, then you come below. So for some theta, cos value will be 1 by 4. We take that theta. Okay, so basically that theta value lies between 0 and pi by 2. So this is u with u is 0 degree, u with v is 90 degree. So now this theta lies between 0 and pi by 2. So this is my W. Okay, what is theta? Theta is the angle for which cos theta equal to 1 by 4. Okay, that is why theta equal to cos inverse of 1 by 4 means that theta is some number between 0 and pi by 2, for which if you apply cos theta, you get cos cancel, you'll get 1 by 4. Okay, so theta is some angle. Okay, now for this now we take a W such that it makes angle this theta with U. Okay, now we got W satisfying this condition. We want to check whether that theta satisfies this condition also. What is inner product V comma W equal to -1? If we take U to be this number and V to be this number and W to be this number, then that W necessarily will satisfy this condition also. Let's see here. We want to calculate inner product V comma W. We want it to be -1. Okay, So inner product V comma W, by formula we get inner product, sorry, norm V, norm W, then angle between V and W. Okay. What is angle between V and W? Angle between U and W is theta. Therefore, angle between V and W is pi by 2 minus theta, because this is pi by 2 and this is theta. Therefore, this is pi by 2 minus theta. That is the angle between W and V. Okay, so I have put a pi by 2 minus theta here. So we get this is equal to norm V, norm W. Cos of pi by 2 minus theta is minus cos theta. So we get minus norm V, norm W, cos theta. This norm V and norm U are equal because all of them have norm 2. So we can replace norm V by norm U. We get this is uh, minus norm U, norm W, cos theta. But theta is the angle between U and W. Okay, theta is the theta is the angle between U and W. So we get this is equal to minus inner product U comma W, but in minus inner product U comma W is equal to minus 1. Okay, so what we have concluding is, in the R2 it is possible to find UVW satisfying all the required conditions. Okay, now since R2 has dimension 2, these three vectors cannot be linearly independent. They have to be linearly dependent. Okay, so we have an example such that this UVW is dependent. So option 4 is wrong. Okay, I hope you understand. This is very important problem. There are many problems in the previous CSR using this inner product idea, especially the fourth one. So I hope you understand. If you have some doubts, please comment. Okay, take care. Thank you, guys.